All right, hi class. Let's get started. We are asked in this first problem to, given a differential equation dy dx equals 2x, and we're given a point on the particular solution to find y when x is 2. This here is a differential equation that we can solve. So if I write dy equals 2x dx, integrate both sides, y is x squared plus c, plug in my initial point, and solve for c. That makes my particular solution, I'll come over here, y equals x squared plus 1, and then at x equals 2, the y value is 5. Okay, so that's nothing really that new. I solved the differential equation, I solved for c, I plugged in the x value that they're asking about, and I found the y value. I actually could find the particular solution that solved the differential equation at that point and find another point. That is not Eulers method. Eulers method is what this lesson's about. There I am, right? Kind of. All right, so here I have a differential equation x plus y given a point 1, 2, and I want to find y when x is 2. Now I made a note here, I'm going to do this with a tangent line approach. So what do you think I mean by that? Well, I know this point here. And I know the derivative at that point is 3. Essentially what's happening is at a point 1, 2, the slope is 3. I can actually find the tangent line. Let's see. I'll go over here and do that. Y minus 2 equals 3, x minus 1. And when I plug in 2, I get 5. And that's my answer, assuming it's not the answer. It's an estimate using a tangent line. I don't know what the curve is that solves this differential equation. I don't know if it's doing something completely different, but the best I can do is follow that tangent line along and get another point. All right, Eulers method. In Eulers method, we follow the following steps to essentially make a bunch of little tangent lines to get from 1 to 2. So I'm going to start off by making a table. And I'm starting at the point 1, 2, and dy dx is 3. I'm going to sketch a little graph right here. Now instead of going all the way over to 2, I'm going to go there in 5 steps, which is my step size. I guess delta x is going to be 0.2. Delta x is changing now. Let's see, the slope is delta y over delta x. So delta y is going to be the slope times delta x. Essentially where I'm going with this is we're going to take this number 3 and multiply it by 0.2, which is going to be 0.6. I'm moving over to 1.2. Moving over 0.2, I would go up 0.6 to get to 2.6. Essentially, on my little graph here, I'm only moving a little bit over, just to 1.2. Now I can recalculate the slope, dy dx, is x plus y. It's going to be 3.8. And I need a calculator. Oops. 3.8 times 0.2 is 0.76. That's my slope at 1.2. If I go over, no, that's wrong. My slope is 3.8. If If I go over 1.4, I'm going to go up 0.76. $3.36. I continue this process until I get to 2. Oh no. So 3.36 plus 1.4, I'm adding those up because that's my differential equation. My slope is 4.76 times 0.2 is 0.952. That's going to tell me my delta y given a delta x of 0.2. So now when I go up to 1.6, 3.36 plus 0.952 is 4.312. Add those up. 5.912 times by 0.2, 1.824. Oh my God, this takes forever. 1.8. Add that to 4.312. 5. So that's 1, 2, yeah. 5.4944 plus 1.8 is 7.29 something times 0.2 is 1.45888. And now I'm finally done. I get to 2. I went over another 0.2. I add that delta y. I should really call that delta y. So add 1.45888 plus the y from before. $6.953. I hope that's right. Alright, I'm going to end this video because it's kind of long. And I gave you a second one with a second example.